Kip, who's going to talk about industrial control systems and cybersecurity risk management. Interesting thing, he went to Dalton Community College for a couple of years, came here, got a computer science degree, then got an MBA. And so now he's really combining all of it together. So we're looking forward to talking, hearing from him and asking questions. The other thing that Nathan has helped us with is in the past couple of years, we've gone to SEL for field trips. We help coordinate those and kind of help them this year are and this year I could work with somebody else, but because of him, we've been able to start that process and continue to do so. So go ahead.
So as mentioned, I came here to school for a computer engineering degree and for an MBA, and I was also in marching band. I happened to go to not the 1998 Rose Bowl, unfortunately, because I started here in 1999, but I did go to the 2003 Rose Bowl. That's when I was in marching band. Last ton of fun. I got lucky because I was in marching band through the early 2000s, where we went to the Sun Bowl, then the Holiday Bowl, then the Rose Bowl, then the Holiday Bowl again. So I got incredibly lucky with my stint as far as football performance went. I also was really excited to walk in this morning and see we're in room 203 of Todd. My MBA program, I had an ICS emphasis, and this is the room I learned about cybersecurity. In fact, when I got hired at SEL in 2008, half of the interview was about my previous job, which while I was an MBA student, I also worked over the libraries as a systems administrator. So half the interview was about that. Half the interview was about the class I took in this room, where I learned about encryption, Excel 509 certificates, all that type of stuff. So I can actually attribute in large part my activities in this room to the job I have today. So I'm really lucky to be here. So as mentioned, I have kind of multiple backgrounds: engineering background, business background. Who here is CS student? Who here is an MIS student? Any others? Any linguistics? Awesome. Any anthropology? Any library science? Poly science? Right? It's kind of interesting the people you run into in the cybersecurity industry because it's a big mishmash of different backgrounds, right? My previous boss was an anthropology major. The only anthropology major I've met in cybersecurity, but that was his background. He was an awesome guy. My current boss is power system. Again, not really something we really expect to see in cybersecurity, but it's becoming a lot more important. When you see the term risk management, for those MIS students, business students, what do you think of when you hear the term risk management? I really want this to be kind of a back and forth discussion. So speak up if you have an answer, speak up if you have questions. I don't want to wait till the end if we don't have to.
It's really hard. We can't hear anything.
All right, I'll speak up.
Thank you.
For the MIS students, what do you think of when you hear the term risk management? Anything? Yeah.
Threats.
Threats. As a business student, I was always taught to associate risk management with insurance, right? As a coder, computer engineer, computer science, what do you think of when you hear the term risk management? I think of reviews, code reviews, right? Making sure somebody else looking at your work that you didn't screw something up, right? So there's two different worlds that, depending on your background, you can really think of that term risk management differently. This is not a presentation on insurance. Don't worry about that. We're not getting into there, right? But what this is really getting back to some of the fundamentals of cybersecurity, right? People who really excel in their fields know and understand and practice the fundamentals every day in their jobs. Why do we care about cybersecurity? There's really three reasons I can think of. One, there's threat actors out there. I'm not going to call them bad guys because they're not all necessarily bad, right? They're doing something at the expense of somebody else to elevate their own status. Maybe they're in economic hardship. Maybe they live in a country where their family's under threat if they don't do something. There's a lot of reasons for people to do malicious things in the cybersecurity world. They're not all bad, right? So call them threat actors. Two, systems we protect are very complex. There's vulnerabilities in them. It's not because the coder intended to put a vulnerability in there, right? You look at the TLS standard, or the TLS implementation, right? There's millions of lines of code in TLS. Look at IPs, there's several 100,000 lines of code in IPs, right? It's because they're complex systems. There's vulnerabilities that get introduced because we as humans are not perfect. 3, there's value in the systems we want to protect, right? If there wasn't value, would we put any effort into it? No, probably not. Right, those 3 things, the value, threats, and the vulnerabilities are really what equate out to being risk in the cybersecurity world, right? Risk is a formula comprised of threats, vulnerabilities, and the consequence for the loss of value. So today we're talking about risk management, cybersecurity, and industrial control systems. We're going to learn about some of the basics about industrial control systems. We're going to try to understand cybersecurity goals in industrial control systems. We're going to look at some of the driving factors behind energy system security and discuss some current trends and solutions. And as a precursor to some of this, some of these slides are a little dated, right? I haven't integrated Tim Schultz's last talk about AI into this, and that's actually kind of a big gap, but this is a longer presentation anyway, so I'm not talking about some of the newest stuff. So the current trends and solutions are really more from like a year, 2 years ago, not what's happening today, because it is moving really fast. Back when I started at SEO in 2008, this came out of a document that was published, I think that year might have been in 2007, the DOE, Department of Energy Cybersecurity Roadmap. And there's a bunch of steps in here, set security goals, identify assets, et cetera, et cetera. There's this feedback loop. Everything you do, you want to try to learn from and integrate into the next time you practice it. And then there's 3 vectors: physical, cyber, and human. Cyber, we're talking cybersecurity, that vector kind of makes sense. Physical. Does physical make sense to be talking about cybersecurity? Yes and no. Right? If you go back to Noel Schultz's talk this morning about the electric grid being cyber physical systems, physical does very much matter. If you look at what an industrial cybersecurity system is, it's mostly machine-to-machine communications working in an automated fashion. There's really not too many humans involved. So if you gain physical access, you're probably not going to be interrupted by a person walking by. Additionally, some of these systems are very easy to access. You go down the hill over here, down to the intersection, there's lights, there's walk signals, traffic control systems, right? On one of the corners of the intersection, there's a big steel box. What's in that steel box? The control system for all those lights, as well as probably communications, either to neighboring lights or back to a monitoring center, or hopefully not, but possibly back out to the general internet. Anybody can walk up to that box and touch the box, right? Anybody can walk up to the box and potentially with a crowbar and beat a hole into it so they can gain physical access to it. Whatever cyber controls you put into an industrial control system, any system, if somebody can gain physical access to it, they can't override or bypass all of your cybersecurity controls. If I get access to a circuit board, I can put leads onto it, and anything that is designed to protect from outside hackers, I can get access to because I'm touching memory directly, and I'm touching buses directly. We need to be aware of that because sometimes these industrial control systems are 500 miles out in the wilderness. The only way to access it is by helicopter. And you can gain physical access to it. And if you know what's there and the communications that are there, you can cause a lot of damage without anybody bothered. Last one is human. Why are humans in here as vectors? Dave, that's why. No matter what cyber you put into place, a human's always going to screw it up. Right? What is the most common attack avenue for any system today? A link in an email. Social engineering. Link in an email. Excel macros. Right? All of those are the most common ways for attackers to actually gain entrance to the system. It's Dave that does it. I hope nobody here is named Dave. I'm not picking on you. So getting more into risk management, there's a lot of steps in here. First is we want to set security goals. As defenders, what do we care about doing? It used to be that, oh, we want to eliminate all cyber attacks. We want to make sure our system is secure, that's proof against anything, period, right? Well, again, going back to something Noel Schultz said this morning, when asked about the resilience slide, we want to predict, we want to know what's coming and protect it in an economic fashion. We can't protect against everything, right? We need to have a good idea of what is coming, the damage it's going to cause, and be able to prioritize what we're going to do to protect our systems. It's not to eliminate all attacks. It is to reduce the probability of a successful attack campaign that's material to the organization, right? I don't care if somebody successfully causes a DOS attack against my firewall, the outside my organization, right? It's going to take me offline for an hour, probably not cause too many significant issues, whatever, right? I do care if they install a backdoor and start leaking information out of my organization, right? That's a much bigger threat that I'm more worried about preventing as a defender. Next, we're going to identify asset systems, networks, and functions. Who here has ever touched a control system? We know what a control system is. Right? You should all have touched control systems at one point. We'll get into that in a second. I'm trying to introduce more humor into my presentations because I'm cybersecurity, I'm an engineer, I'm an introvert, right? People sometimes have trouble creating rapport, right? So one thing I'm trying to do is put more humor into my presentations. I couldn't find a comment for what is an industrial control system. So first time ever, I went to ChatGPT and I said, hey, generate me a comic. And this is what it's generated, which is why you can't read any of the words. And, right? So I just find this really, really humorous using ChatGPT and giving it very, very minimal prompt, right? But I think it's funny. The more do I look at it, the more fun it is. But industrial control systems are all around us. Planes, trains, automobiles, right? You touched a car. You ever use cruise control in a car? That's a control system. Right? You ever use a coffee pot? That's a control system. Power plants, gas, oil pipelines, refineries, food processing plants, traffic system, right? All of those are control systems. Really simple control system, probably all of you have touched. Maybe you got yelled at by your dad because you turned the temperature up when you were cold. Is the thermometer on the wall? There's one over there, right? A control system is a system that is cyber physical. It's measuring the physical world, doing some processing on that information, and then causing a feedback loop, causing output to then affect the physical world. In the case of a thermostat, we're reading the temperature. If it's 71 degrees and we're set at 72 degrees, we trigger voltage to go to the furnace to raise the temperature in the room. We hit 72 degrees. Hey, we're at our set point. We're going to turn off that voltage to the furnace. It's going to turn off. Very simple. How often does a user interact with a thermostat? Almost never. Maybe daily. Historically, almost never, right? I remember as a kid, every time we wanted to touch the thermostat in the house, we had to find the instruction manual because we never remembered how to set it. Every single time. Right? Because they're not designed for users in the system. And that's historically what control systems are like. You set it, you forget it, you touch it again in 10 years when something's broken. Different kind of control system. The analogy here breaks down a little bit, but this is a circuit breaker in your house or your apartment. Everyone's probably seen one of these at one point. What it's doing is the same as that thermostat. It's measuring the current going through the circuit breaker. That current spikes, gets too high, 15 amps, 20 amps in a home circuit breaker, then it'll trip and cut energy. So we don't have excessive heating, we don't have a potential fire, we don't have somebody who has licked their fingers and stuck them in the wall socket, die or get hurt or whatever, right? We trip it for safety reasons, for the house, for the people, right? Very simple analog system. Looking at the broader power system, we do the same thing, but we don't use the little simple circuit breakers because we're not talking 120 volts or 30 amps. We are talking 500 kilovolts and thousands of amps, right? This is a picture of an SEL 421 here. This is something my company produces. We look at what's going on the power system, right? We're looking at the voltage of the power system through PTs, potential transformers. We're looking at the current that's going on through CTs or current transformers. And then we have an output. We control circuit breakers or tap banks or transformers or whatever else, right? If everything is normal, great, we just let it go. If there's a fault on the line, as indicated by the red arrow there, we recognize there's something wrong. The voltages we're working with, it is a life safety critical issue. We have to trip that breaker to make sure that somebody doesn't die or the power system itself doesn't burn out. This has to happen very, very quickly and very, very reliably. So you might ask, what's the fault? Well, here's an example of a fault, right? It is an arc. It is a short between phases, phase to ground, dual phase. It is a voltage sag. It is a frequency drop. There's a lot of things that can be considered faults. What happens if you don't clear a fault? You can see there's a lot of energy there. When there's a lot of energy, things heat up. Those wires will melt. Those wires melt, it's gonna be a long time to restore power, right? So we want to trip that breaker, even if it's not a life safety issue, it is an asset protection issue. Very first, well, the birth of the electric grid can be considered to be, I don't know, 1892, I think, in Folsom, California was when the electric grid got started. I don't have pictures of power relays from 1892, but I do have a picture of a Westinghouse protective relay called an electromechanical relay from 1902. This works almost exactly the same way that the circuit breaker in your house does. For 82 years, we worked with the analog system on the electric grid. It works well from a safety perspective. It does not work well from a visibility perspective. In the 70s, if you had a power outage, you had to call the power company and say, hey, my power's out, right? And after they get enough phone calls, they might figure out where that fault was, where that breaker tripped, and be able to restore power. But it's going to take a while. In 1984, we have the first digital protective relay ever, right? At this point, we start having the ability for communications. This was a probably 16 megahertz processor with a 1200 baud parallel port in it. You didn't do much communications with it, but we started generating data for what's happening on the grid. We started generating event reports and fault locations, so we knew where on the line the fault might have occurred. And it is the start of modern protection systems. Progress now to 2024. What's up there is the SEO T400L, much more powerful system. We're not talking 60 megahertz processor, we're talking 800 megahertz processor. Not one parallel port, it's got 4 gig Ethernet ports, it's got 2 serial ports, it's got USB ports, it's got a lot of communications. Not only that, it's got probably 24 communications protocols in it. Right, and I'm showing you this because in 1984, devices were stupid simple, right? It was hard to screw them up. It was hard to put vulnerabilities in them because everything was custom made. You had minimum lines of code. Most of the 1984 box was written in assembly, right? In 2024, there's millions of lines of code in that box. It becomes more complex, becomes potential for more vulnerability. There's also potential for more misuse from users. From an operator's perspective, nowadays we have big, huge walls. One lines of the electric grid on there. And all of the data that all of our relays are producing get piped back to the operations center. And it immediately flashes on the wall green if a breaker trips. Normally they're red. You might think that's backwards. I did. It took me a long time to get used to it, right? But red means not safe to touch, right? Power's going through it. Green means safe to touch. Power's not going through it. It's not in its normal optimal state. Prior to having communications, you'd get a phone call from a customer who says, hey, power's out, and you walk up to the wall and put something there. Okay, we know it's out here. Then a few minutes later, you get another phone call. Okay, we can move that fault up this direction in the line. A few minutes later, you get another phone call. Okay, we can move up to this direction in the line, right? So it took a long time just to isolate faults. Nowadays, we can do it in near real time. One thing that I think is really interesting about working in industrial control systems, especially the energy system, is the longevity of the technology that's there. I can go into any substation today, a number of my customers, and see serial communications and frame relay and SONET and Ethernet and satellite and POTS, plain old telephone dial-up, all in one substation. I've been in substations where on the left side of me is a SONET ring that goes 500 kilometers. SONET's very high-speed deterministic technology, right? I know for a fact that any packet I put on that ring is going to come back and hit me within 5 milliseconds, right? On my right side, satellite communications, very non-deterministic, not high performance, right? It's not going to be 5 milliseconds before I get the packet back. It might be 2 seconds, it might be 5, it might be 20, depends on where the satellite is, how many retries are needed, what the atmospheric effects are, right? It is weird working in those environments where you have completely different design expectations on both sides because the system evolves over time. Once something is in place, you don't remove it until it's broken. There's 2 families of technologies we talked about. Previous presenters already hit a little bit on these today, right? In IT technology, we have highly dynamic environments, right? Think of the college campus, a bunch of people living in dorms, doing research projects for all the different classes. You never know what websites they're going to get, right? Whereas in operations technology environment, it is almost all machine-to-machine communication. You know this relay is talking to this relay and nothing else, right? You know exactly what's happening. In IT worlds, we have a tech lifespan of 3 to 5 years. In operations technology, I put 10 to 60 years. 10 years because my company warranties our products for 10 years. That's our minimum expectation for how long it should last in the field. 60 years because I've had customers tell me they have a replacement cycle of 60 years. If they don't have a failure in 60 years, they're not going to touch that device. They're not going to remove it from service. So anything I build as provider of equipment for energy systems, I have to think about that 60-year lifespan. When it comes to cybersecurity, that means there's a lot of ramifications for the technology that I choose to put in that box. Is there a crypto expert in here? How long is modern day RSA crypto supposed to last? With the advent of technologies that we're proposing, right? Is it a year, is it 2 years, is it 5 years, is it 20 years? With the advent,
we all have to change our passwords every 6 months, so.
that's a good plan, yeah. For crypto, right, if we're talking like RSA, PKI crypto, everything today is secure, but with the advent of quantum technology, quantum processing, the expectation is all of that RSA stuff that PKI and X509 is built on is going to be useless in somewhere between 5 and 10 years, right? Don't know if that's accurate or not, but that's what the quote experts are saying, right? Which means if I put RSA into my product today, it's going to be a huge burden on my customer to update that, on me to update that over the next 50 to 60 years, right? I can put technology in today that's only useful for 5 years, right? But also understand that they need it for 60 years. It creates a really big problem in some cases. IT is best attempt. One way to show this is the SMTP, Simple Mail Transfer Protocol. Its current standard for SMTP says to keep retrying to send emails for up to 7 days, right? If I'm talking a real-time protection system that needs a packet to get across the network in 5 milliseconds or less, otherwise it's useless, right? That IT technology does not work in this life, right? We are failure intolerant, right? Paul Schultz had that slide on resilience, right? We cannot have faults. It is the life of a person, the safety of the system, potentially the economics of the entire US if we're not really careful with that with failure conditions. IT is data-driven, OT is machine-driven. IT is in controlled environments, OT is in uncontrolled environments. What I mean by uncontrolled environments versus controlled is I create a server for Facebook. It's going in a data center that's air conditioned, that's filtered, that's a really nice, cool environment for computers to sit in. I build a relay to protect the power grid. Where's power? There's transmission lines in the Sahara Desert. There's power systems in Antarctica. My equipment has to exist and work in operating conditions, ambient temperatures of minus 40 degrees C to plus 80 degrees C. That limits the processing I can do. Right, so I don't have the power in my equipment to do the same technology, and the same processing that the IT world does. That's another one of the challenge points of doing cybersecurity in OT. So now you know a little bit more about the assets, the systems you might see in industrial control system environments. We can start assessing the risks. Another comic. Anybody heard of Little Bobby before? Anybody know who Robert M. Lee is? He's the owner and founder of a company called Dragos. They do intrusion detection and prevention systems, threat hunting. Robert actually came from the US government doing threat hunting for the Air Force. And so he comes from a federal background, doing analytics about foreign adversaries. And he created this comic. This is part of his company, Dragos, and he's been producing it for a long time. And I really like this particular line. We could really use some basic IT support. You go into an ICS system, depending upon the entity, the utility that it might be. This is a very true statement. I need basic IT support, right? If you go over to Wenatchee PUD or Lincoln County PUD, for a better example, right? They've got 2 guys that do the power system, they do the automation of the power system, they do communications, they do the NERC compliance. 2 guys do all of it, right? They don't know enough to do any of it. So they're constantly working with vendors, constantly working with contractors, figure out what to do, right? They need basic IDs. Right, so that is a big problem in a lot of the industry. As far as vendors go, though, and I have to admit, I have done this at times as well, is we want to make money for our company, right? And that's not by going back to basic IT support. That's by building the next generation of cybersecurity products, right? That's by doing pen testing services, right? The last slide on here is how about a risk assessment, right? You can see the engineers trying here, right? This one I actually think is really awesome as well, because he's trying because he doesn't consider basic IT support, right? But if we go back to my introduction to this presentation, that is a fundamental cybersecurity, right? If you don't know what your risks are, if you haven't assessed your risks, you don't know what you need as far as basic IT support. You don't know if you need a simple firewall, right? Risk assessments are critical to do upfront. Components of risk, I already talked about this, threat, consequence, probability. We are trying to reduce the probability of the occurrence of a risk, right? And threat you can kind of break up into both threat actors and vulnerabilities. So the threat actors, traditionally we talk about 4 threat actors, level 0 or accidents, right? This is Dave, right? Level 1, garden variety, these are what we refer to as script kiddies. People that are curious, just poke around, don't know they're going to cause damage, but still cause damage anyways. Level 2 are mercenaries. These people actually have some intent to cause damage because they have some economic gain from it. And then level 3, nation states. We tend to refer to nation states today as APTs, advanced persistent threats. What do I care about as an ICS cybersecurity defender? Nation states. I don't care about mercenaries. I don't care about garden variety. I don't care about accidents. I've got to take on nation states. If I can successfully defend against nation states, I can defend against all the rest as well. The nation states, they have tremendous resources, tremendous amount of money. They have tremendous pressure they can put on engineers or their citizens, right? But they're not very likely to actually do it, right? I'm not picking on China here. I want to say that out loud. I'm not picking on China, but use China as an example. Maybe they are in our power systems. Maybe they have made some way to gain access. They are not going to do anything damaging because they want to stay there until there's a global conflict with the United States. But at that point, they might make their presence known, right? So there's very low likelihood of them actually doing anything damaging because they don't want to be kicked out of our systems, right? Until that global conflict happens, then it becomes much more likely they're actually going to do something. The threat landscape, yes.
Yeah, one of our speakers yesterday, Dan Brown from CySER.
Yep.
Mentioned Volt Typhoon.
Yep.
Is that kind of sounds like what you're referring to? Does SCL, like, are you involved in like hunting for those kinds of things?
No, we do not do threat hunting ourselves. I leave that to the people who specialize in that. That's something we've talked about getting into, but no, we recognize there's other experts in the world about that, and we have partnerships with that, so we're not about to break. But we do not do those types of investigations ourselves. So those are the threat actors. The threat landscape is constantly changing. Right? On the left here, we have increasing ICS vulnerability landscape, right? And that kind of goes back to that evolution slide I told you, where in 1984, we introduced digital, pretty minimal, right? We've progressed in the capabilities and complexity of those systems, and the vulnerability landscape is increasing because of that. We have connections to untrusted networks. Industrial control systems were designed to be not connected to anything, to be completely isolated. However, you have corporate interests in getting metering data so they can charge their customers as fast as possible, right? So for that metering data, they need to have connections from the power system into corporate, right? You have contractors who come in and like, oh, I need to work on this thing, but I'm out of town, I'm out of time right now, and I got a flight early in the morning. I'm gonna put in this remote access point so I can do my work back from my office, right? And we'll remove it in a week, right? Do they remove it in a week? Nah, it gets forgotten about because it's not documented. Now you have a persistent backdoor in your system, right? That does happen pretty regularly. There's the human factor. We discussed Dave already. Intrusions into the supply chain. Back in 1984, yeah, we were starting to see a global supply chain, right? Today, I cannot make any product that is not purely software-based without the help of Taiwan and India and probably China, right? We're trying to bring a lot of it back home to the US as a nation, right? But I cannot build anything that other countries being involved. That means there's a lot of opportunities for foreign nation states to get into the supply chain to affect the design of code, affect the design of chips, put malicious actions in there, put backdoors in there, actually put time bombs in there. Right? There's a lot of opportunity for that now. There's a significant lack of detection capabilities. This one is significantly changing in the past few years, right? I mentioned Dragos. Dragos is doing much better at this point, right? However, we are starting to see, well, not even starting, we're in the middle of a bunch of efforts to actually reduce our detection capabilities, which is really weird. I'll get into that in a minute, right? And then there's more and more demonstrated attacks, right? Cole Schultz mentioned Stuxnet, probably a couple of other things as well. To get into the value proposition, of why we're doing cybersecurity and the threats, right? And the risk. This is I can never remember the name of this. This is the dam in Russia in 2009. This is the generation facility, the top floor, right? So you can see all these knobs in the middle of the floor. Those are the top of generators. Each of these generators is 150 tons, 300,000 pounds. Each of these generators can produce 650 megawatts of power. This entire generation floor, I think, has 10 generators in there. This whole floor, to replace it with wind power, would require 6,500 wind turbines, right? That just kind of gives you a scale of what you can do there. Another number for scale, this floor here with these 10 turbines that generate 6.5 gigawatts is enough to power 5.5 million homes in the US. The US home average usage is about 1,200 kilowatts, or 1,200 watts, 1,200 kilowatts, right? So 5.5 million homes with generation capacity in this facility. In 2009, there was an incident here. It was not an attack. This was Dave. One of these, actually, before we get to that, a little bit more about what a hydro plant looks like, right? So hydro plant has a dam. Top end, you have a reservoir. This is where all the water is, right? You go down on the North Clearwater. We have the Rorschach Dam, longest straight access dam in North America. Huge reservoir there. I've taken a tour there. It's actually pretty cool. If you get the opportunity, I highly recommend it. There's a big reservoir there. Then you have the dam, and in the dam, you have the control gate, which allows water into the penstock. Penstock channels the water into your turbine, which rotates the generator and then exits through the exhaust down to the river below treatment, right? So the turbines in that dam were under maintenance. They were locked in position. They were not able to rotate, and the control gate was closed. A control operator, through the HMI with his mouse, accidentally opened the control gate. Now we're talking, this is a 300 or 150 ton generator, right? What's going to happen when you have a ton of water pressure from reservoir hit something that is super heavy but can't move? It causes a catastrophe. That 150 ton generator shot through the roof. Only place you could go was up, it shot through the roof. Completely destroyed the dam. Completely destroyed power of 5.2 million homes, right? Billions and billions and billions of direct damage to the dam, billions and billions and billions of damage to the economy of Russia, right? Now, if I was an attacker and I found a system that would even accidentally let me cause this kind of damage, oh man, that's a gold mine, right? I'm sitting on that for as long as I possibly can, right? But it goes to show you that even though this wasn't an attack, I mean, there's a lot of value there. There's a lot of damage that somebody who wants to cause harm could actually cause. Some other examples, I'm not going into these. You can Google them if you want to. Merseyside was an incident in Australia where someone had unauthorized access after they were fired. Stuxnet, Noel Schultz mentioned that the Natanz nuclear plant had virus installed on it through USB. Metcalf is a substation in Southern California where somebody was shooting transformers, and that's at the same time they cut communications lines. And then Ukraine on December 23, 2015 was a precursor probe to the invasion of Ukraine. This caused a lot of conversation around the world when Ukraine happened. I would recommend going to Google and looking those up. I'm not going to them now in the interest of time. Next, how to prioritize things. Well, I don't have a lot for prioritization. There's a lot of different ways you can prioritize things. Go back to an old comic, Gilbert, and I just kind of realized that, I might be dating myself a little bit just by some of the comics I'm picking. But here we have Alice teaching a ship how to prioritize. Right? What do you choose to do? Well, how much do you hate the person that asked you to do? More realistic way to prioritize is using the Eisenhower matrix. Where you break things into, are they important or not important? Are they urgent or not urgent? If they're important, do it. If they're not important, probably not going to do it well, whether it's urgent or not, right? And then if it's urgent or not urgent, if it's urgent, do it now. If it's not urgent, you can delegate, contract it out, right? It doesn't have to be done this instant, it can be done in 6 months, find somebody else who has more time for it, right? I am constantly prioritizing in my work when we're analyzing vulnerability fixes, bugs, field findings, et cetera, for my products, right? We have to prioritize on a number of different things. Is it important? Well, One easy metric, unfortunately, which we have to use because a lot of our customers rely on it, is CVSS scores. Right? When I say it's a very poor metric, because CVSS scoring system is really designed for IT systems, not industrial control systems. It also has a bunch of assumptions built into it. That this is a standalone device that we're talking about, not systems of devices that are relying on each other. But that's one metric we use. Another is this exploitable? Can somebody actually be reasonably expecting to find this and exploit it in the field, right? That would generally make it urgent. Next, we start to implement protective programs, and this is where most of my career has been, is in protective programs. Thou must patch, must encrypt all protocols, must implement all controls in 62443, right? There's a lot of people that say you've got to do everything. Right? Kind of going back to goals and vendors in the prioritization piece is you got to do what's economically feasible, what's going to be the most impactful to reducing the probability of a successful attack. There's a bunch of guidance out there. Paul Schultz mentioned some of these in RIPSIP. She went through in detail. I'm not going to go through those. But as a side note, my first day on the job at SEO was January 13th, 2008. My third day on the job, I was in New Orleans at the San SCADA Summit. The same day RIPSIP became law. So I've been dealing with it my entire career. Then there's ISA, IEC 6443, 6351. These are very much more technical standards, whereas something like RIPSIP is much more procedural and policy-based. Both good to know. But going through any of those, you'll learn about a bunch of defensive strategies, and you probably already know about some of these yourselves, right? You know, what's the first thing you start trying to think of as a cyber defender? Well, how can I deter someone from getting into my system, right? My system is too hard to get into. They're going to find something easier. That doesn't work against nation states, right? Nation state has a target. They're going to hit that target. They're not going to go find something easier, right? Next is detect. We need to be able to detect what's going on, right? So we want to put in some monitoring capabilities, some data correlation capabilities, backups, et cetera. We want to be able to know what's happening in our system. We want to isolate and contain incidents, right? Going back to microgrids, that's a great technique to isolate power system events, right? Same thing with cybersecurity. We want to be able to isolate incidents. If we can detect physical intrusion at a substation, let's kill the communications from that substation until someone can drive out and see what's going on, right? Can contain that event for that site. Defensive strategies are not just putting in a firewall. And even doing this for 15 years, even having a huge focus on industrial control system security for 15 years, I still see a lot of the time where people think, oh, just put a firewall or just put intrusion detection system, right? Cybersecurity ultimately is policies and processes. We need to keep that in mind. The technologies should be in support of those policies and processes. We see a lot of reusing IT technology in the OT space. Some good, some bad, right? Syslog, actually pretty good. It's a great way to send messages across the network for security, reporting, operational purposes, right? Pretty basic. On the flip side of that, TLS. I already mentioned TLS. You can kind of imply those bad when we talk about lifespan of OT devices, right? TLS 1.0 is in usage in the early 2000s, right? Not long after I started SEO, we went to TLS 1.1. We went to 1.2. Now we're at 1.3. The standard itself changed 4 times in 15 years. That can't happen for a device that's expected to last 10 to 16 years. Can't do that, right? Additionally, TLS 1.3 does not allow authentication only in cryptography. It only allows for encryption protocols, cryptography, encryption protocols, cryptography, right? Yes, there's authentication there too, but I can't turn off the encryption, just have authentication. What this means is, if I'm being forced, per some of those standards I just referenced, 62351 is IEC in support of goose messaging, which is another ICS standard. 6150, which requires end-to-end cryptography between all of these goose devices, right? 62351 requires you to do that via TLS. If one of those devices gets compromised, I can't use an intrusion detection system to see that compromise in the network because everything is encrypted. The attacker can live off the land. The attacker can hide in my own defensive strategies. And if we know what's going across the network, if this is machine to machine, we really need to consider the application. Is this information that must stay confidential, or can it be plain text? Most of the information in the industrial control system, in the power system, is public information. I can buy an SCL relay, I can plug it into the wall here, and I can tell you 99% of the data that's going on in that substation. Cost me $4,000 in a few minutes of my time. Right? We don't care about protecting the vast majority of that data. Now, if we look at, these devices have been there for a while. Some of those devices might be from the 1980s, 1990s, use Telnet for engineering access, plain text protocol. Someone uses that to log in remotely and issue their password. Password's plain text. Yeah, that we want to protect. Right? But forcing everything to be TLS means you're actually hurting your own defensive strategy because you're limiting the tools you can use. X.519, great technology for protecting web applications. I am an entity that is completely self-contained. Do I need public key infrastructure to secure my communications channels to authenticate my other devices? Actually use it? Sure. Should I? Maybe, maybe not. I've seen plenty of instances where engineers, again, the one-man shop does everything. He's not a crypto expert. He's been told he needs to do TLS with X.519 for authentication. What's he do? He creates certs that are 60, 100-year expirations because he has to learn it. He doesn't know what he's doing. He doesn't know best practices. And he's got the mindset, well, my devices are going to be there for 60 years, so why does the crypto not be there for 60 years too? And on the flip side, I'm going to be retired by the time I advance detection, so I'm not going to have to do it, right? I've seen that behavior multiple times. That's a training issue, one. Two, it's a misuse of technology. Something else really should be designed that's more appropriate for these environments. There are a lot of IT technologies that can be reused or reinvented for industrial control systems. I mentioned there's 4 gig Ethernet ports in that T400L, right? We're using a lot more Ethernet than we used to, and there's been a lot of hesitance to do this in the industry because Ethernet is non-deterministic, to go back to Tim's talk, right? We don't know what's going to happen with an Ethernet system because all of the switches, all of the routers make their own best guess at what to do with the packet that comes in. Oh, I think based upon all my different links that are up at this given time, it needs to go out this time, right? Maybe it'll work, maybe it won't. If that link breaks, if a link dies, it takes time for the system as a whole to reconverge. Generally, with modern technologies, with blanking on the term, with spanning tree protocols, it's 5 milliseconds per hop, right? Software-defined networking gets rid of that distributed control of Ethernet, right? And maybe you're familiar with SDN, maybe not. It was invented, I guess invented, at least standardized by Stanford back in, I don't know, 2008, 2010, something like that, in the form of OpenFlow, popularized by Facebook because Facebook recognized that existing networking technologies were not sufficient to handle quick dynamic changes in their loads on their virtual servers, right? So they started adopting SDN, building their own switches to have this central control that knows, oh, I've got this virtual load that's spinning up over here. I need networking to it. I'm going to completely rearrange the network instantly from the central standpoint that has a holistic view of everything to make a best in case decision as fast as possible, right? We can take SDN and instead of using it for the dynamic nature like Facebook does, we can use it in a very static fashion. If I know my network, if I know all the communications flows, I can say this relay here, talk to this relay here and force it at every node in the system. If that device talks to that device, nobody else. I can specify protocols. I can even specify payloads at some point. It's still using Ethernet, right? I don't need to change the Ethernet in the end devices. I don't need to change the router. I don't need to change the intrusion detection system. All of that can still be used. This is just a restructuring of how Ethernet in the network is controlled. MACsec. MACsec is a layer 2 encryption technology, right? If you want to talk about ICS, it's layer 3. If you talk about TLS, it's layer 4. On the OSI networking stack, MACsec operates at layer 2. It's link layer. It encrypts from one switch to the next switch or one device to the next device. It is really powerful because if I need this link to be encrypted, I can encrypt everything on it. But then this link over here, it's unencrypted because it's going to an intrusion detection system, right? So I can get the best of both worlds, of both encryption and intrusion detection. MACsec also has something really powerful I've never seen in anything else. It can selectively encrypt packets. So if I'm in that situation where I've got Telnet in my system, and the system recognizes, oh, there's a password going through in this packet here. That's secret information. It can encrypt that packet, but leave everything else unencrypted. Right? Really, really powerful technology. We always want to be thinking about the system level when we talk about industrial control system security, right? It's not a device. There's a bunch of components here. Here we have a Purdue diagram that shows all the levels. At the bottom, we have level 0, physical. These are your analog devices, so CTs, PTs, transformers, breakers. Level 1 is your relays, your real-time protection equipment. Level 2 is automation. Still near real time, but we can have delays there. And then we have the users of level 3, right? Level 3 is one designator of your DMV, DMZ. Level 5 is the other. In the middle there, we have level 4, which is your DMZ. This is where humans generally would interact with the system. They don't need talk to the relays directly for the most part. They need access to the data. You export the data out to the DMZ, that's where users interact with the system. That's how, one of the ways we can protect this data. Right? So we need to think about it at a system level perspective. Each of these different levels has different cybersecurity technologies that might be appropriately applied. You have to think of the application you're trying to protect, right? Protection level, I don't want anything that's going to add latency. Right? At the DMZ to corporate data flow, I probably care a lot more about confidentiality there as well as user-based access controls. And then people do touch all the levels, so we need to think about them all. Last is measuring effectiveness. You say we're meeting a goal. Well, what's our goal? I mean, it's going to be specific to an organization. Generally, I want to increase my company's stock price, right? That's generally my goal. Right? But from a cybersecurity perspective, it's very hard. My first day on the job, I was also tasked with trying to figure out cybersecurity metrics. Incredibly difficult thing to do. Maybe a company has the goal of saying, hey, let's reduce the successful attacks against us by 10% next year, right? How do you know if you did that or not? Do you know all the attacks that happened against you this year? Did you detect all of them? Maybe next year the global stage is different and you're probed far less. Did you really reduce the number of attacks against you through your efforts by next year by 10%? Or was it just because there was less activity in the world stage? You don't know. It's almost impossible to know if you're meeting goal. So what we do, instead of setting arbitrary metrics, is we test. Right? We design our systems, we design redundancies, we design incident response plans, we do tabletop exercises, we test our backups, we do penetration tests. Do not ever do a penetration test on a live industrial control system, right? You might accidentally shut off the power to all the things. Right? Don't do that, right? Instead, build what's called a digital twin, right? Simulate that system in the cloud, somewhere else, offline. Do your tests against that simulation. Don't do it against the live system. And there's a lot of unique considerations for ICS. Most of cybersecurity revolves around IT world, right? We have to flip some things on their head. We have to take other considerations, know the impacts of misusing a lot of this IT technology. You need to be aware of the applications. If you're not tuning your security to your applications, you're probably going to fail, right? Either because you caused problems or because you didn't actually secure what you thought you were securing. It's a very challenging environment for cybersecurity, and there is tremendous room for innovation. My boss just did a talk at S4 this year, which is going to be publicly available in August. I highly recommend to look for it. His name is Nick Seeley. His presentation was, is cybersecurity really a physics problem? It's a great talk. I'm just going to leave you with that. Hopefully you look it up when it becomes available. But it's really trying to get to, are we at the fundamentals of cybersecurity? I mean, I kind of argued we were talking about risk management today, but is that really the fundamental, right? And you could argue no. IT systems were designed to move anything, period. If we tuned all of our technology to the applications, would cybersecurity really be more concerned? Maybe, maybe not. I don't know. But I encourage you to look at that talk and discuss it yourselves. So thank you for listening. Appreciate it. Are there any other questions? Yes.
So you mentioned a lot of your central licenses are, they were, seems like they're on like these lines, right?
Again, yep.
Are you switching now to just some sort of overlays or back a few years or something?
We are, something I didn't talk about here, well, I mean, initially, earlier on, and I also didn't talk about is cloud is starting to become something. Right? There's been a big push, always do not connect to the internet, right? Well, now AI is one reason, right? We're starting to think maybe connections to the cloud are might be acceptable. right? In general, though, land is completely owned by the utility or contracted out with their ISP to be dedicated line that nothing else will cost. However, distribution systems where you might have a reclosure control out on a pole on the street, right? They don't often have communications, right? So they have to start using things like cell phones. We do use VPNs regularly when it goes over public infrastructure, but it's not commonly used when it's all over private infrastructure. Yes.
I was really intrigued by what you showed about Japan.
Yeah.
And, it seems like it's a major vulnerability across the border.
Yeah.
What can be done to protect those systems, from, somebody, the nation state bombing, somebody to make this happen?
User experience is really what needs to be redesigned. These systems were designed with the assumption that they'd be isolated, that Dave and Dave alone is going to be able to access them. Right? They were not designed with the assumption that, oh, there might be a cell network or Ethernet or anything like that. Right? And 20 years ago, 30 years ago, when all this stuff was starting to be built, communications was slow, was minimal. People would probably not have really significantly imagined cell systems being used to carry data. They barely existed. Right? So the assumption was it's going to be isolated and trusted, educated, trained people are going to be there to use it. So we're going to give them an easy method to use the system. Right? I got a mouse, I've got a screen, I can click on buttons. Real easy to use. What we didn't think about was, okay, well, accidents, well, malicious actors. The dam here, Subayo Shushinsky Dam or something like that, was an HMI issue. Clicked on the wrong button on the HMI. I just moved the mouse around. Ukraine, which I didn't really go into, but Ukraine, December 23rd, 2015. There is strong evidence that was also an HMI issue, right? The attackers got in, to go into more detail now. The attackers got in, and I think via email, but I can't remember. They managed to create a backdoor. They found the Active Directory server. They elevated access on the Active Directory servers to give themselves more powerful credentials for the whole system. They found the HMI computer, remote desktop into the HMI computer. And legitimate operators see the mouse moving around on the screen when the attackers were in there. They're like, what's going on? We don't know what's going on. This is weird. It's behaving. It was an attacker in the system using that HMI, right? And really one way to do it, which probably haven't done in most places yet, if anywhere, right? Is to make it impossible to issue a control, without typing a password or without typing a badge or without some sort of authentication on that control. Right? We want them open for monitoring capabilities. But if I'm going to click a button, maybe we need a scenario where I scan my CAC badge within 5 seconds of issuing that control, right? And that'll do a lot to prevent at least the attackers from getting it. It may not do a whole lot for Dave, right? The other way to do it is doing something called dual control, right? If I want something to happen in the system, I need to accept it, and then Dave needs to accept it, right? Both of us need to click our buttons, I don't know, within 5 milliseconds, 5 seconds of each other, right? If we both don't do it, well then I screwed up, Dave screwed up, we didn't agree, something happened, right? Whatever, it doesn't actually happen. At the same time, it becomes problematic to do some of that because sometimes these are life safety critical systems. And if the automated portion of it didn't work, I need to be over there and hit that stop the gas button on the wall, right? And if I can't do that by myself, if I need James to walk up here and hit it right next to me, right? That means there's more risk in the life safety system. We're not gonna be able to respond as quickly. So it's kind of a catch-22.
Well,
Yeah.
Tuesday, we're visiting SCL here in Pullman. Will you see you there?
I will not. Unfortunately, I'm flying to Boise Wednesday morning. So I'm making it too. I live in Vancouver and I lived in Pullman for 12 years from 99 through 2011. Moved to Bothell and Kirkland and then down to Vancouver. So that's where I'm at. I'm here 2 days and then